Yeah, then let's continue with our second talk by Fabio about efficient approximate triangle counting. Please take it away.
Okay, thank you. I'm Fabio Vandin. I'm from the University of Padova in Italy. And in our group, we work on algorithms for, let's say, data analysis in general. And we often strive to get to three goals. One is to have algorithms that can scale to very large data sets. Two is to get some theoretical guarantees on the results of our algorithms. And three is to actually have the algorithms that can be implemented in practice. So they shouldn't be too difficult, at least for us, to not introduce too many bugs in our code. So we're not always able to achieve all three goals. But today I'm going to present a work on the analysis of triangles in temporal networks that hopefully I will convince you is achieving all three of them. This work also is in some sense related to some of the questions of the morning sessions, where we were asked whether we could be less pessimistic about what we are doing, in the sense that very often we look at worst case analysis. And some of the research we have been doing recently is about trying to go beyond this worst case analysis by using predictions. So in the algorithm with predictions framework, as you will see. Okay, so what I'm going to present is actually joint work with Giorgio Venturin, that is a PhD student of mine, Ilya Sarpe, that was a PhD student of mine and is now a postdoc at KTH. And actually, they are the ones that have made the first version of the slides. So if they look good and there are no typos, is what they have done. If you find typos or error, I'm the one that introduced them. Okay, so I guess we don't really need to say why counting triangles is important. It's a fundamental primitive in many applications. Yeah, I wanted to point on the slide so they see it on Zoom as well, hopefully. Yep. Okay, so that's counting triangles is a fundamental primitive in graph analytics for many applications. Okay. And now we're interested in temporal graphs, and just to, without getting into many of the details, since we have heard many times the definition, we're going to look at these temporal graphs where on the edges we have labels that represent the time of the events. And in fact, in our representation, we assume that an edge includes, an edge is a directed edge, and it has a temporal label that represents the time for that edge. When we have multiple labels on one edge, actually, we usually represent that as two different edges. And so when I talk about an edge, I remember that there is a time associated with it. Let's see if I can. Okay, so the triangles we are interested in are these temporal triangles. And so what they are informally, again, they are graphs that are triangle shaped. And they have an ordering among the labels on their edges. Okay, so since we are having directed edges and we have an order on the time of the events for the three edges, we have a total of 8 different triangles that we could be interested in. Here in this representation, for example, for triangle type T1, we have that at time T1, we have first the interaction between the orange edge and then the green one. Then T2 is between the blue one and the green one. And then T3 between the orange one and the blue one. Okay, and so that's the order of the events we are interested in. Then for T2, what can change is the direction of an edge. And for the other ones are directions and also order of these three edges. Okay. So we focus on occurrences of triangles in a temporal graph. And in particular, we focus on the definition of occurrence given by delta instance that has been introduced in 2017, where we're given a parameter delta that is essentially the maximum time between the first event, the first edge in the triangle, and the last edge in the triangle. Okay? And so in general, we have a delta instance if we have a triplet of edges that form a temporal triangle, and the duration of the triplet is at most delta. So for example, if these are the edges in our temporal graph, we have that we are interested in the temporal triangle of this type. So the order on the edges and the direction of the edges is as shown here at the bottom right. then we have that actually 3 edges that are highlighted in red here on the left represent a delta instance, for example, for delta equal to 20, since the first edge appears at time 1 and the last one appears at time 11. Okay, so this is the definition of delta instance, and we can now, define the problem we are interested in. That is, we want, given a temporal graph G, so the time again is in each of the edges, process the streaming, that's one of the things we are interested in, and the time duration delta. We want to find the number of delta instances in the temporal graph of each of the 8 temporal triangles. Okay, so that's what we want to compute. So for example, if this is our temporal network in input, our output would be the counts below here that you find for the different temporal graphs. For example, this temporal graph here appears twice, this temporal graph here appears once, and the other ones do not appear with a time restriction of 20 in our graph. Okay, so we are in the streaming model. So we assume that at each time we observe only one of the edges, or actually we're given the next edge in the order given by the time. And since we have the maximum duration delta for triangles, for instances of triangles, it means that when we are looking at a stream of edges, actually we can look at a time window that contains edges within a time window of length at most delta. Okay, so what has been done in terms of counting triangles in a temporal graph? Well, there are several exact algorithms that are based on different properties. Here are also the references. And they obtain exact counts. Most of them are not algorithms for the streaming model. And recently in 2025, actually after we published the work that I'm describing, a new algorithm for exact counting in streaming and counting all the temporal triangles has been published. However, these approaches, even the one that came after our publication, they are essentially impractical, either because they require too much memory, or some of them, again, they do not work in streaming, so they're not particularly efficient. Okay, in terms of approximating the number of triangles, really, the state of the art is EWS that provides an approximation in streaming by exploiting uniform sampling of the edges and wedge sampling as well. Okay. The main issue here is that this approach, that has also nice theoretical guarantees, does not really scale to very large, massive temporal graphs and can only estimate one triangle at a time. And so it doesn't fully address the problem we are interested in. Okay, so just to summarize, the challenges that really we are facing when trying to solve our problem is that we want to look at really large networks. That's what we're focusing on. And so the current methods require a lot of time and also a lot of memory. We don't have random access to the data since we are doing it in streaming. We really want to minimize the number of passes on the data. Ideally, we want to make only one pass. And we want to have a small memory budget as it is standard in the streaming model. Since we are resorting to approximations, and we will do it with sampling, that is a technique that we use a lot in our work, these estimates may have a very large variance, okay, depending on whether you sample good edges or not. Okay, so our goals are to have an algorithm that computes the estimates for all the 8 types of temporal triangles efficiently, and to provide highly accurate estimates, as accurate as possible. And so what we're going to do then is to design a one-pass streaming algorithm, so that it really requires only one pass on the data to estimate all the triangles simultaneously. And to have accurate estimates, we're going to try to exploit predictions to improve the estimates of the quality. And I'm going to soon tell you what I mean by predictions, or what are the type of predictions that we assume. In fact, our contributions is first of all the design of an algorithm that we call the STEP. That is a single pass streaming algorithm that employs predictions. You can think about predictions from some machine learning model, but you will see that actually we suggest something very simple to do that, to estimate all the temporal triangle counts simultaneously. We then have the theoretical analysis of our algorithm in terms of the quality of the estimates. In particular, they are unbiased. We have also some results on the variance. on the memory requirements under perfect and noisy predictions. Perfect predictions are not really achievable, but it's just a way to understand how far we could push the improvements if we had great predictors. While instead of the noisy ones, we believe they model what you can get in practice fairly well. And then we also design a practical predictor that is efficiently computable and is really domain agnostic. So it doesn't assume that you have any specific feature for your graph that may be domain specific. Finally, we have performed an experimental evaluation of our algorithm that shows that it really outperforms the state-of-the-art approaches, and this scales to very large temporal graphs that have billions of edges. And so in the remaining of the presentation, I'm going to describe the algorithm, try to give you an idea of the theoretical guarantees, and also tell you something about the experimental evaluation. Okay, so let's start with an overview of our algorithm STEP. STEP, that stands for Streaming-Based Temporal Triangle Estimation with Predictions, has really two main phases that are iterated over the stream of edges. We sample edges of the graph stream, and we do it continuously as the edges arrive. And then every time we get a new edge, we also estimate the number of triangles that are closed by the edge that arrives. When I say triangles, I also mean the ones that are delta occurrences, so that they satisfy the delta requirement of having the first and last edge in the triangle being not far more than delta in time. Okay, so where do we use predictions? We really use prediction in the sampling phase, since we used a predictor that is going to try to tell us what are the heavy edges. What are heavy edges? Where they are really, they provide us with the natural information that is important when you count triangles. That is the edge that I'm seeing now involved in many triangles or not? Okay, so that's the overall idea. And using this prediction, we can decide to keep some of these edges in main memory, or if instead we're going to just sample them with some probability. Using the prediction, this allows us, if the predictions are good, to reduce the error of the estimates compared to what you get with naive sampling approaches. Okay, so let's see a toy example of how STEP works. And what we do is every time we see an edge in our stream, we first use the predictor to decide whether the edge that we see is heavy or not. Heavy means it is involved in a lot of triangles, and otherwise it is a light edge that is not involved in a lot of triangles. So if the edge is heavy, then we keep it, we store it in our main memory, in our, let's call it sample, for sure, deterministically, with probability 1. Otherwise, we sample it with the probability P that is fixed. Okay? So for example, let's say the first edge that we see is this edge V2 to V3 at time 1. Then we ask the predictor, is this an heavy edge or not? The predictor says it's not heavy. And so what we do is now we sampled with some probability P, and it happens that actually this edge is not kept in memory, is discarded by our sample. Then the next edge that we see is V3, V4. And we ask the predictor, is this an heavy edge? The predictor answers yes, it's a heavy edge. Then we store it in the main memory, keeping in mind it is an heavy edge. And we save also its time, since it's needed for the delta, to make sure that we have, to understand what type of triangle we observe. And then we keep going, so we get another edge, V3 to V1 at time 3. Predictor says it's not heavy, but then maybe this edge is sampled with the probability P, and so it's added to our sample. So what we have is that after seeing the edges, what we keep in main memory are some edges that are labeled as heavy, and they are deterministically in our main memory. And then we have some other edges that are really the result of a uniform sampling process with some probability P. Now, when we get a new edge, for example, the edge V2, V3 at time 25, what we do is we count how many temporal triangles and of the different types this edge closes, looking only at the edges in our sample. Okay, so for example, V2, V3, it's an edge that was from V2 to V3 that has time 25. And so what we really need to do now is to look at all the edges that go from V2 to its neighbors, V3 to its neighbors, and we only need to to look at the neighbors that are common among the two. And just by looking at these edges, we can find all the different types of temporal triangles and update the counts that we have. Okay, now the update of the counts must take into account also whether the edges are heavy edges or not. So for example, if we just seen the edge V2, V3, and this closes a triangle with two heavy edges, we know that we are seeing this triangle deterministically because heavy edges are placed in my memory with the probability 1. So we're going to update the count for the corresponding type of triangle by increasing it by 1. And that's what we do when we have two heavy edges. If instead you have a triangle that you are closing that has one heavy edge and one sampled edge, then you increase it by 1 over p. And if you have instead a triangle that is made of, well, the edge that you just seen and two sampled edges, the two in green here, then you know that you're sampling it with probability p squared, and so you need to update the count by 1 over p squared. Okay, so this is the way you update the counts, and so at every time you have an estimate of the number of triangles of the different types that you have seen up to now. Okay, so what's the predictor that we suggest to use in practice? Again, we wanted to have something that we could implement, so not just have a theoretical predictor. Okay, so what we consider was some simple information that you really can get for any graph, that is the degree of a node, also including the time information. Okay. In particular, since our goal is to identify edges that are contained in many delta instances, the idea was to look at edges that in a given delta, in a given window, have many neighbors for one of the two, for both vertices, as a proxy for the importance of that edge. Okay, and in particular, we are gonna essentially say that an edge is heavy if both its nodes have many edges that are incident to them in our time window delta. This can also be computed very efficiently because you are keeping you can only look at the time window of delta and update the counts for all these vertices, so that's something extremely quick to compute. Okay, so a bit more in details. We can define the temporal degree of a node within a time interval TATB as the number of edges that have one of the two nodes of the edge as the extremes in that time interval. And then we define the temporal minimum degree weight of an edge for a time duration delta as the minimum of the temporal degrees of the two vertices for the edge. Okay. And then our temporal mean degree predictor is going to classify an edge as heavy if the edge is among the top k edges ordered by the temporal minimum degree weight, and otherwise it's going to say that the edge is light. Okay. So we're trying to mimic the information of whether the edge is involved in many triangles or not. We cannot compute this information exactly, otherwise we have already solved the problem of counting triangles. And so what we do is we use this minimum degree as a proxy. So for example, at time 7 and for time duration delta equal to 5, if we look at the edge V2 to V1, we see that V2 has a temporal degree of 2 within the time interval 212. And node V1 has a temporal degree of 3 within the time interval 212. And so the temporal mean degree of this edge is equal to 2. Okay, so that's what we compute. And the ones that have high weight, then they are the ones that are predicted as heavy by our predictor. Now, is this a good proxy for heavy edges or not? So we look at real data, and what you see here are for three different, or actually for different data sets, 4 different data sets on the row. And for 3 different values of delta, you can think about them as small delta, medium delta, and very large and large delta. On the x-axis, you have the actual heaviness in how many triangles an edge is involved in. Each point is an edge. And on the y-axis, you have our proxy, that is the temporal mean degree. So you see that there is a correlation between the two, but of course, this is not a perfect information that we are using. However, it's very fast to compute, so hopefully it's going to give us something useful that you can use in practice. Okay, so That's the predictor that we are going to use. However, before getting to the practical evaluation, let's look at some of the results of our analysis. So I'm going to give, I guess, only the informal results. So first of all, what we could prove is that if you have a perfect predictor for heaviness, then you have that the variances of the estimates provided by our algorithm are of the order of p to the minus 2 m delta. M delta is the maximum number of edges in a delta time window, is how many edges you have to consider at most during the execution of the algorithm, times the cardinality or the number of triangles of a different type Ti. Okay, so this is what you get if you have the perfect predictor. Now, this should be compared without what you can get without the predictor. So you have no information and you just sample uniformly at random. And what changes is instead this term, cardinality of Ti, instead of being there with degree 1, is there with degree 2. So actually the variance can really decrease by a lot by using a perfect predictor. Again, this is with the perfect predictor that is not practical. Okay, but before getting to the results for noisy predictors, we can also prove that the memory can be that our algorithm requires is sublinear if you have a perfect predictor. So you can use sublinear memory and obtain a relative epsilon approximation for all the quantities that you are trying to estimate if your probability of sampling is large enough. Okay. Now, what happens if instead of having a perfect predictor, you have a noisy predictor? Instead of getting to the details of the result, let me tell you what is the model for the noisy predictor that we are considering. So what we are assuming is that if you look at all the edges sorted by the heaviest one to the lightest one, so from the most important one to the least important one, what our predictor can do is makes very good predictions for the heaviest edges, so you recognize them as heavy. Makes very good prediction for the lightest edges, so recognize them as very light. In between, can make arbitrary errors. So around the threshold for whether something is heavy or not, the predictor can make arbitrary errors in there. So now we can also analyze the results for this noisy predictor, and what you can really prove is that if your probability P of sampling is large enough, so if you keep enough edges, the memory required by the algorithm is still sublinear under the assumption that the count is large enough. So if you need to count to obtain a count that is very small and you want a relative approximation, that you need tons of memory, of course, but otherwise what you can get is that the memory that you require is sublinear in what you would do without the predictions, even with the noisy predictor. Okay, so now let me get quickly to the experimental evaluation. So in our experimental evaluation, we tried to answer different questions, and in particular, we compared the step with state-of-the-art methods in terms of accuracy and computational resources. We asked what's the impact of the predictor on the estimates, and maybe more interesting, we try to understand how the algorithm performs in an online setting where you learn the predictor on some portion of the data and then you use it for future data. Okay, so first the baselines we compared our algorithm with are the 5 state-of-the-art methods. For the last one that came out after the paper, we have now a journal version that we are going to submit soon, for which we have also the results. We also compared with naive sampling, where you don't have the predictor, just to see how naive sampling compares to the state-of-the-art and also to the use of the predictor. So as predictors for our algorithm, we look at the perfect predictor. Again, this is not practical because you're already solving the problem, but just gives us an idea of what's the improvement of using predictions as we are doing in our algorithm. And then we have the practical predictor, that is the one that I described before, the temporal minimum degree. So it just looks at the minimum degree of an edge within a time window and uses that proxy for heaviness. As dataset, we consider 4 of the largest available temporal graphs. That these are the numbers. You can see they have millions of nodes and up to billions of temporal edges. And we tested 3 values of delta, small, medium, and large. And so we run it on a system with 200 gigabytes of memory. And what you can see here is a table with the memory required by the different methods, okay, for the 4 different data sets in terms of gigabytes that are required. And this last row in particular is for the largest data set. And you can see here that all the exact methods and also the currently available approximation method, they get an out-of-memory error. While instead we require 63 gigabytes, that is not a small value, but at least it's doable for this very large data set. Okay. In terms of running time, here you have the different methods. So here we only look at step with the temporal mean and degree predictor, the different deltas for the 4 different data sets. And you can see that our method is usually the fastest one. The fastest, the lowest time is highlighted in bold for all data sets, and all data is the fastest one other than for this configuration. And if you look at the speed up compared to the other methods, is usually a speed up that can vary between, let's say, 10 and hundreds of times. Okay. Now, if we look instead at the accuracy, and here then we are comparing our method step with different predictors. The perfect predictor is the one with the triangle in yellow, on the temporal mean degree. We are comparing it with naive sampling and with EWS. What you see, these are the 8 different triangles. This is the mean absolute error for the methods, so the lowest, the better, the lower, the better. You can see that adding the predictor always helps. And also the temporal mean degree usually leads to an improvement compared to naive sampling, and in particular compared to EWS for different data sets and different values of delta. Okay, and this is a similar result. And then let's move to the online setting. So in this online setting, again, we have the stream of edges. And we use the first portion of the data to learn a predictor, really to learn a threshold for which to say if an edge is heavy or not. And then on the remaining part, the last part, we run our algorithm and we see how it performs with now information learned only on the first part of the stream. In particular, we use 75% of the edges for learning the threshold, and then the remaining 25% is the data for which we estimate the number of triangles. And we compared it here with the naive sampling that really is the main competitor here. And so what you see here is that the predictor that is learned on the first portion of the data outperforms the naive sampling in most cases, even if in some cases can give predictions that are worse than naive sampling when the predictor provides information that is actually not really reliable. However, even in these cases, the difference between the two errors is not too large. Okay, and these are similar results for other data sets. And since we really wanted to be fancy, we also used as a predictor a simple neural network to see if it will give us something better. You see that sometimes it improved compared to the temporal mean degree, but not very often. Maybe that the reason is that we are not using domain-specific information. However, there is at least a predictor that you can really learn with the machine learning method that you can try to see how it works with our algorithm. Okay, so in conclusion, what I presented is STEP, that is a single pass streaming algorithm to estimate all temporal triangle counts simultaneously. And we have some theoretical results about the quality of the variances of the estimates that we get and how they improved thanks to the predictor. And also how the memory is lowered by using a perfect and noisy predictions. We also propose a practical and domain agnostic predictor that is quick, can be computed efficiently. And this leads in practice to have a method that outperforms state-of-the-art techniques, in particular for very, very large graphs, temporal graphs with billions of edges. Okay, so that's it. And I would be happy to answer questions. Thank you.
Thank you very much. Are there any questions? Yes.
So did I understand it correctly that the sampling is mainly there to bring the working space down?
It's there to bring the working space down, yes. That is the main one of the main problems of these algorithms when you get to very large graphs.